Hello everyone. So in my previous concept I discussed about electromotive force. Electromotive force is defined as the work done by the source in taking a unit positive charge from its lower potential to higher potential. Its SI unit is volt. So how we measure the EMF of a cell? Suppose if you take a cell, so to the cell nothing is connected. It says it's an open circuit itself, means no current is drawn, current is not drawn through the cell. Now if I connect voltmeter across the cell, now voltmeter reading is showing so around 9 volts. So this 9 volt we define as the EMF of cell, EMF of source equal to 9 volt. So when no current drawn from the circuit or for a open circuit, so the potential difference across the source is defined as EMF of the source. So EMF stands for electromotive force, but in reality it's not a force, it's the potential difference when there is no current is drawn. So here we define one more quantity, that is nothing but battery resistance or internal resistance. For a given cell, if we can increase the internal resistance, so the internal resistance is also we define. How we can define the internal resistance? Suppose this is a cell composition, say a positive pole, copper will act as positive, and another a zinc rod, and here electrolyte is diluted H2SO4. So this is the electrolyte. Now when the circuit is on, so it means the current is flowing. Now external, the current is flowing through the circuit, but when we see the current, to flow the current in a closed circuit, now this is a closed circuit. Now we can show the direction of current. Current will flows from the positive to the negative. So that is the direction of current, which is I marked with as white. Suppose if we can take the electron direction, so the electron direction is opposite to the direction of the current. So these are the direction of the electrons. So the electrons will flow from positive electrode to negative electrode. So during the motion of the ions and the electrons, so ions will move opposite direction to the electron directions. So there is a possibility, not possibility, we can say that, so the ions and electrons they will collide. So ions, Zn plus ions and electrons, so they collide each other. So this collision cause resistance. So here the resistances happen inside the cell. So this we termed as internal resistance. So that is we define as internal resistance. So this internal resistance is purely depends upon the electrolyte. So the characteristics of the internal resistance also purely depends upon the electrolyte. If you change the electrolyte, the internal resistance value changes, and if you change the concentration of the electrolyte, the internal resistance also changes. If you can decrease the distance between the two electrodes, the internal resistance value changes. Not only that, the temperature. So when the temperature increases, the internal resistance is decreases. So this internal resistance only occurs in the source of the given. So today, so let us derive a relation between internal resistance and EMF and external resistance. So I would like to derive the relation between EMF, internal resistance, and potential difference V. Consider a cell of EMF E. So this is the cell which is having EMF, we are representing that EMF E, and internal resistance. Internal resistance equal to small r is connected to external resistance capital R. So that is the external resistance capital R we connected. So if you draw a circuit diagram, so we need to draw circuit diagram that carefully. Now, so if we represent this everything as a cell, so this is a new change what we learned in the previous class. So this is a setup of cell. So here the small r is represented, it is positive terminal of the battery, so it's a negative terminal, and this is r small r, and this everything we call as cell. Now to the cell, if I connected an external resistance, suppose this is the resistance we connected across, and this everything is connected via wire, and this capital R is the external resistance, and current is flowing from positive terminal to negative terminal. So this is the I is the amount of current which is flowing through the circuit. Now let me consider at here 2 points, capital A and capital B, across the cell. So that is the 2 points I considered here, capital A and capital B. So this is the entire circuit diagram for what's shown in the above picture. Now here we define as EMF. So EMF is defined as EMF E equal to work done by the cell. I will write that. Work done by the cell in carrying a unit positive charge. In carrying a unit positive charge along the closed circuit. So this is the definition of the EMF what we defined. Work done by the cell in carrying a unit positive charge. So this is the I belongs to the circuit, so I can represent that at here. Yeah, work done by the cell in carrying a unit positive charge along the closed circuit. And at here EMF we define as, so the positive charge is carrying in the two ways, from the A to B outside the cell and from the B to A inside the cell. Therefore this EMF E equal to work done in carrying a unit positive charge in carrying a unit positive charge from A to B, from A to B, that is the external circuit. External circuit, or I can write that external resistance, that is a good word. The external resistance, capital R. plus, so this along plus work done in carrying a unit positive charge from B to A against internal resistance. So here two resistances are there. One is external resistance, so that is represented capital R, and another one is internal resistance. So this is we were representing with small r. So if you write this expression mathematically, suppose if I can take that EMF E equal to V plus V dash. So here V is the work done in carrying a unit positive charge from A to B. So that is also we defined as potential, and here V dash is the work done in carrying a unit positive charge from B to A against the internal resistance capital R. So here I need to find out what is V. So we can find out that by using Ohm's law. By Ohm's law, so from outside, what is Ohm's law? V equal to IR. So here I is the amount of the current which is flowing in the circuit. So I is the amount of the current which is flowing in the circuit, and R is the external resistance. So therefore here V itself, therefore V itself becomes V equal to IR. So in bracket I will represent that this is external resistance. And for V dash, which equal to same current also flowing through the circuit, to the whole circuit, the current is same. The amount of current through the whole circuit, that is remains same. But through the cell, now in this case the internal resistance R value gets changed to small r. So here it is the internal resistance. Therefore we can write that EMF as, so EMF E equal to electromotive force equal to, we can substitute these two values, IR plus I little r. Now let's take out I common, so we can end up R plus small r, capital R plus small r. So from this I can write, hence the current in the circuit, I got expression for the current. So if we can make it equal of these two, EMF E and the corresponding expression I times R plus R, just make it equal these two and write the expression for current. So the current I equal to, therefore equal to I of capital R times little r, therefore I equal to EMF upon capital R plus little r. So this is the expression for current. So here we included the term, what is that? Internal resistance. So this is the relation between capital R and EMF and internal resistance along with current. Now the terminal potential difference. Now the terminal potential difference of the cell is given by. So here I would like to define what is terminal potential difference. I think if you know this is terminal potential difference, well and good. So this terminal potential difference, we define this as, the potential drop across the terminals of a cell when a current is being drawn from it. So the potential drop across the cell of EMF E and internal resistance of EMF when a current is being drawn, when a current is being drawn. So if the circuit is connected in a simple manner, I can explain it here. If the circuit is connected with external resistance R, now this is the cell, so this is up to the cell. Now to this cell an external resistance R is connected. After connection, if we measure the potential difference across these two, if I connected the voltmeter and if I measure the potential difference after connecting to the external resistance, so what is the voltage shows across the cell? So this potential difference we term as terminal potential difference. One more time I am repeating. To a cell, if we connected an external resistance, so in that case current is flowing, current is drawn. So in that time, if you measure the potential difference across the cell, so what is the potential difference we get? So that is we define as terminal potential difference. Now in this case, to measure the terminal potential difference of the cell, so because through the cell current is flowing, so we can represent that terminal potential difference as V. So if V is the potential, I is the current and R is the resistance. So here V we define as terminal potential difference. Now let us substitute the value of current I from the above expression. From the above expression we can get I equal to E upon capital R plus little r times again the resistance R, since I equal to E upon capital R plus small r. So if we can write this everything together, if I write that expression everything is together, therefore V equal to E times EMF E times and capital R upon, so capital R times small r. So this is the expression for terminal potential difference. So this is the terminal potential difference is also nothing but the work done by the cell to moving a unit positive charge from A to B. So in my expression, so I am having V at here. So we define V, that is the work done in carrying a unit positive charge from A to B. So that we have taken as V at here. So this is also known as terminal potential difference. Or from here itself we define the terminal potential difference. So from here itself also we define the terminal potential difference. So from here, suppose I take from this one, so from A, So from here you can write that expression for V. Therefore V equal to EMF minus V dash. So EMF minus V dash. So this is also we defined as terminal potential difference. So better I will write this expression at down so that the both will be looks at one location. So or terminal potential difference, or since EMF E equal to V plus V dash, therefore V equal to EMF minus V dash. So here V is also nothing but terminal potential difference. The potential difference across the cell after connecting the external resistance R. So here we define terminal potential difference. I can write in a simple equation form. So terminal potential difference equal to, from this mathematical equation I can get that EMF minus potential drop across the internal resistance. Here V dash is nothing but potential drop across the internal resistance. So this is one more definition for the terminal potential difference. Potential drop. So this I express from the above expression. Now from this expression we can easily write the expression for internal resistance. We need to write the formula for internal resistance R. Therefore terminal potential difference V equal to EMF minus V dash. Since V dash equal to I times internal resistance small r, therefore V equal to EMF minus I times small r. And we can write that small r expression. So therefore I will rewrite this expression. I times small r equal to EMF minus V. Therefore R equal to EMF minus V upon I. So this is the expression for internal resistance, and EMF and V is the terminal potential difference and I is the amount of current which is the flowing through the circuit. So if we can rewrite this expression again, so by substituting I equal to V by R, therefore small r equal to E minus V upon R. Since I is here, I equal to, I can write that in bracket at here, by using Ohm's law, V equal to IR. So this is the potential, terminal potential. Therefore, if we can simplify that expression, and R equal to EMF minus V upon V times R. So here don't be get confused at all. So this is, I will write that characters. So here R is internal resistance and E is the EMF and V is the terminal potential difference and capital R is the external resistance or load resistance. Now this is the formula for internal resistance. Here small r equal to internal resistance and E equal to EMF and V equal to terminal potential difference and R equal to external resistance. Now let us see for a special case. So that special case is when cell is open. When cell is open, it means there is no current is drawn from the cell. Open circuit means there is no load is connected. So when cell is open, I can mention that I equal to 0. So in my circuit, I can draw only this much. So there is no external load, only cell is present. So in that case, when the current equal to 0, if we can write this expression from the above expression, if we can take, so in this expression, if we can substitute that value, so if we can take that from the internal resistance R, since R equal to EMF minus terminal potential difference upon I, so if you can rewrite that, I times R equal to E times minus V. Since I equal to 0, so this left hand side becomes 0, it becomes EMF minus V, which also equal to EMF E equal to V. Here the V is nothing but open circuit. So the potential difference becomes open. So this is what we define as EMF. How we define as EMF? If there is no external source is connected, the potential difference across the cell is defined as EMF of the cell. So when there is no external load is connected, obviously the current value becomes 0. So that is what happened at here. I equal to 0. It means in this external load, this load R, it is not connected. I'll make a cross. So that is R equal to 0. When R equal to 0, we will take this expression. So current is not drawn. So I can remove honestly that expression, sorry, that circuit element. I can leave up with only the cell. So if I take R and if I can substitute I value equal to 0, since it's an open circuit, current is not flowing. So we will end up EMF equal to the potential drop across the cell. Now here if we connect one voltmeter, now just connect a voltmeter across the cell. So what is the voltmeter shows? So that is the EMF of the cell, since current goes to 0. But if you can take another case, in this special case, a real cell always has some internal resistance. So a real cell, not any hypothetical cell, a real cell always has some internal resistance. A real cell always has some internal resistance R. So when current is being drawn from cell, therefore we have the terminal potential difference always less than the EMF of the source. So this is what happens due to because of the internal resistance. So that is the potential difference across the terminals of the cell in a closed circuit always less than the EMF of the cell. That is the potential difference across the terminals of the cell in a closed circuit is always less than its EMF. So these are the two special cases in this present scenario. So finally, I can conclude that the internal resistance of a given cell expression in terms of EMF, and here V is the terminal potential difference and I is the amount of the current which is the flowing. So from that expression we define the terminal potential difference or open cell. So when there is no current drawn, so the terminal potential difference which equal to the EMF of the cell.